Hello students, we were seeing the point basic current voltage relationship. So in last lecture we have seen the different symbols and nomenclature of the transistor, that is PNP and NPN transistor. The three different configurations, that is common base, common emitter and common collector configuration of the transistor. That is, in common base configuration, the base terminal is common to input as well as output. For common emitter configuration, the emitter terminal is common to both input as well as output. And for common collector configuration, the collector terminal is common to input as well as output. In the next diagram, we have seen the schematic of PNP transistor connected as an amplifier. Then in next diagram we have seen the doping profile of the transistor, and then we have seen the band diagram for the normal operating condition of the transistor. So we will continue in this lecture. So from the continuity and the current density equations, the steady state characteristics are given, and for the neutral base region, these equations are given by, from the continuity equation one may write 0 is equal to minus of P minus PB upon tau B plus dB into dou square P by dou x square. This is equation number 1, and from current density equation one may write for the whole density Jp is equal to minus Q into dB into dou P by dou x. This is equation number 2a, and for the electron current density, Jn is equal to J total plus Q into dB into dou P by dou x. This is next equation number 2b. So in these equations, PB in equation number 1 is nothing but the equilibrium minority carrier density in the base. This P is the carrier density of holes. J total in this equation number 2b is nothing but the total conduction current density. Tau B is given in this equation number 1 is the minority carrier lifetime, and dB, which is given in equation number 2a as well as 2b, is nothing but the diffusion coefficient. The conditions at the emitter depletion layer edges for these excess carrier concentrations are given by the equations P dash of 0 is equal to P dash of 0 equal to P0 minus PB, which is equal to PB into exponential of VB by KT minus 1. So this is next question number 3, and n dash of minus XE is equal to n of minus XE minus NE, which is equal to NE exponential of VB by KT minus 1. So these two equations comprises equation number 3. So in this equation NE is nothing but the equilibrium minority carrier density in the emitter. A similar set of equations can be written for the collector junction. So these are the equations for the emitter junction. So similarly we may write for the collector junction P dash of W, which is equal to P of W minus PB, which is equal to PB into exponential of VCB by KT minus 1 and n dash of XC which is equal to n of XC minus NC, which is equal to NC into exponential of here must be Q, I have forgotten, exponential of Q into VCB by KT minus 1. So these two equations comprises equation number 4. So this equation number 3 shows the set of equations for the emitter junction, and this equation number 4 gives the set of equations for the collector junction. The solution for minority carrier distribution, that is the whole distribution in the base from equation number 1, and the electron distribution in the emitter and collector are given by P of X which is equal to PB plus into square bracket P dash of W minus P dash of 0 into e raised to minus w upon lb divided by 2 sin hyperbolic of w upon lb into e raised to x upon lb minus into bracket p dash of w minus p dash of 0 into e raised to w upon lb divided by 2 sin hyperbolic of w upon lb into e raised to minus x upon lb. So this is equation number 5, where this w is the width of depletion layer and lb is the diffusion length in the base. Again, for the electron distribution, one may write n of x is equal to ne plus n dash of minus xe into exponential of x plus xe upon le for x is less than minus xe. This is next equation number 6, and the electron distribution in the collector is given by n of x is equal to nc plus n dash of xc into exponential of minus x minus xc round bracket complete upon lc for x is greater than xc. So this is equation number 7. So equation number 6 gives the electron distribution in emitter region, while the equation number 7 gives the electron distribution in collector region, in which Le is the diffusion length in emitter and Lc is the diffusion length in collector. So this diffusion length Lb is given by Lb is equal to under root of tau b into dB, tau b into dB, where this tau b is the lifetime of carriers in the base and dB is the diffusion coefficient. So this LB is the diffusion length of holes in the base and LE and LC are the diffusion lengths in emitter and collector respectively. So the equation number 5 is important because it correlates the base width W to the minority carrier distribution, and if this W tends to infinity, then or when this W tends to infinity, the ratio W upon LB is greater than the 1. So when this happens, the equation 5 reduces to P of x is equal to PB plus P dash of 0 into e raised to minus x upon LB. So this is next equation number 8. That is when this W tend to infinity or when this W by LB becomes greater than 1. So for this condition, this equation number 5 reduces to this equation, and which is identical to the case of PN junction. So in this case, there is communication between emitter and collector currents which are determined by the density gradients at x is equal to 0 and x is equal to W respectively. The transistor action is thus lost, and from this equation number 2 and equation number 3 we can obtain the total DC emitter current as a function of applied voltage, and the total DC emitter current is given by IE is equal to A into JP at x equal to 0 plus A into Jn at x equal to minus xe, and which is equal to A into value of Jp is minus q into dB into dou p by dou x at x is equal to 0 plus A into value of Jn is minus q into dE into dou n by dou x at x is equal to minus xe. So this can be again solved as IE is equal to A into Q into dB PV upon LB cot hyperbolic of W upon LB into exponential of QVEB by KT minus 1 minus 1 upon cos hyperbolic of W upon LB into e raised to QVCB by KT minus 1 bracket, round bracket complete. Then here square bracket complete. Plus A into Q into D NE upon LE into exponential of QVEB by KT minus 1. So this is next equation number 9. And for the total DC current, again similarly the equations can be given as, for total DC current, IC is equal to A into JP at X is equal to W plus A into Jn at X equal to XC, which is equal to A into the value of JP is at X is equal to W is minus Q into dB into dou P by dou X at X is equal to W plus A into value of Jn at X is equal to XC is minus Q into DC into dou N by dou X at X equal to XC. So it is equal to A into Q into dB PB upon LB into 1 upon sine hyperbolic of W upon LB into e raised to q into VEB by KT minus 1 minus cos hyperbolic of W upon LB into e raised to q into VCB by KT minus 1. Bracket complete. Square bracket complete. Minus A into Q into DC NC upon LC into e raised to q VCB by KT minus 1. So this is next equation number 10, which gives the total collector current, and in this equation the capital A, here I have written this A, is nothing but the cross-sectional area of the transistor, and the difference between the two currents is small and appears as a base current, which is given by IB is equal to IE minus IC. So this is next equation number 11. So we shall now modify the doping distribution in the base layer in the figure of doping profile, and consider more general base impurity distribution, and I will draw here the figure. So for this doping distribution, here on y-axis the acceptor or donor distribution density is plotted, which is Na plus and Nd plus and Na minus. This is donor density, which is given by Nd plus, and Na minus is acceptor density. On y-axis is plotted, and on x-axis the distance is plotted. So this is the space charge region or depletion region at the junction. And this is the space charge region at the junction J2. So a transistor with such doping distribution is called drift transistor, and since a built-in electric field enhances the hole drift in the base, the donor density and the electron density in the base, that is donor density is given by capital N and electron density is given by small n, and the relation between donor density and electron density will be capital N will be greater than small n, and it is given by this small n equal to capital N, which is equal to Ni exponential of Q into psi minus phi upon kT. This is equation number 12. Where this Ni is the intrinsic carrier concentration, phi is the Fermi potential, and psi is the intrinsic Fermi potential. So from this equation number 12 we obtain the built-in field, which is given by built-in field is given by epsilon is equal to minus d psi upon dx, which is equal to minus kt upon q into 1 upon n into dn by dx. So this is equation number 13. And the whole current density Jp is given by Jp is equal to Q into mu b into P into epsilon minus Q into dB into dP by dx. So this is equation number 14. Substituting this equation number 13 in equation number 14, we get by substituting this equation number 13 in equation number 14, we get the value of Jp as Jp is equal to minus Q into dB into bracket P upon N into dN by dx plus dP by dx plus dP by dx. This is equation number 15. So the steady state solution of this equation number 15 with boundary conditions P is equal to 0 and X is equal to W is given by P is equal to Jp upon Q into dV into 1 upon nx 1 upon n of x integration over x to w n of x dx. So this is next equation number 16. So the whole concentration at x is equal to 0 is given by P at x is equal to 0 which is equal to Jp upon Q into dB into 1 upon NBO integration over x to w n of x dx, and which is nearly equal to PBO into exponential of Q into VEB upon KT. So this is next equation number 17, where this NBO is the donor concentration at x is equal to 0 and PBO is the equilibrium whole concentration at x is equal to 0. So the NBO into PBO is nothing but Ni square, where Ni is the intrinsic carrier concentration and the current IP which is equal to A into Jp, where A is the area and this IP, current IP is given by IP is equal to Q into A into dB into Ni square upon integration over 0 to W n of x dx into exponential of Q into VEB upon KT. Or this IP is again can be written as IP is equal to IL into exponential of Q VEB by KT, and this is next equation number 18, in which this IL is nothing but Q into A into dB into Ni square upon integral over 0 to W Nx dx. So the total collector current IC is given by IC is equal to IL into exponential of Q into VEB by KT plus I2 plus I2. This is next equation number 19, where this I2 is the saturation current. So next we will see the figure of typical experimental results. So these experimental results, the current in ampere on y-axis and VAB on x-axis. So current is plotted along y-axis, current in ampere, and voltage, that is VEB, is plotted along x-axis, VEB in volts. So this plot shows the 4 different regions due to the variation in the current as a function of VEB. .2, 0.4, 0.6, 0.8, 1 and 1.2. This is saturation current I2. So this is the difference. This difference is N into IB. This is the region which gives RB into IB, and this region is called drop region. This region is called drop region. Then this region is called high injection region. High injection region. This is the ideal region. Ideal region. And this is the non-ideal region. Non-ideal region. So these are the points for the variation of current as a function of VEB. That is, this is the variation in IB and this is the variation in IC. So this is given by minus exponential of Q into VEB by KT. And this gives the exponential of Q into VEB by KT. So this is minus exponential of Q into VEB by KT, and this is Q exponential of Q into VEB by KT. So this figure shows the typical experimental results. The exponential law of given by equation number 19 is very closely obeyed over the most of the current range, except for very high current densities where the injected carrier that is injected carrier density becomes comparable or larger than the collector doping concentration. So the constant IL can be obtained for the extrapolating the current to VEB is equal to 0. The number of impurities per unit area in the base, which is also called as Gummel number, can be obtained from equation number 18, and which is given by QB is equal to integration over 0 to W n of x dx, which is equal to Q upon IL into A into dB into Ni square. This is equation number 20. And for silicon and BJT, the Gummel number is about 10 raised to 12 to 10 raised to 13 per centimeter square. This Gummel number is 10 raised to 12 to 10 raised to 13 per centimeter square for silicon BJT. And this figure, that is, this is figure number 5, which shows the typical base current characteristic, and is observed, they are observed the 4 different regions. That is, this is the non-ideal region, this is the ideal region in which the transistor is working, this is the drop region, and this is the high injection region. So with this I will stop here. Thank you.